Okay, welcome to Math 150, Lecture 28, 2021, Section 1. And what we're going to be doing today is talking about Green's theorem and reviewing some of the sequences in series. We're at the end of the semester, and so I want to make sure we have plenty of time so that if you have questions about the material, we can go over them. And several people have asked me to talk a little bit about the key tests for convergence. And so I'll talk a little bit about that, and then I'll shift to Green's theorem, which is a great way to review some of the integration we've done. So convergence. When you are trying to determine if the sum converges, what is the first thing you should check? Good, does AN go to 0? And it is necessary for AN to go to 0 for the sequence for the sum to converge, but it's not sufficient. So we've seen the harmonic series before. So the key tests, we have the comparison, we have the ratio, we have the root, and we have the integral. And when we're looking at the integral test, typically you replace n with x, so almost always that will work. And you need to know what the conditions are for the different tests. So for the integral test, you want a sequence where the terms are either non-increasing or non-decreasing. And the integral test will not only talk to you about whether or not it converges, but it will give you a sense of what it converges to, a good approximation to the value. And you're not going to be off by that much. And if you want, with a little bit more work, you can actually get some really good estimates as to how close you are. The comparison test, in some sense, is the easiest one to use. So whenever I'm asked you, which one do you want to do first, I want to do the comparison test using the method of divine inspiration, where I just happen to write down the right thing to compare it to. And if you show that you are term by term less than a series that converges, or less from some point onward, I don't have to start at 0. I could start at some big integer, and I don't care what's going on in the beginning. If I can show that from some point onward, I'm always less in absolute value than something that converges, I converge. Or if I can show from some point onward, I'm always greater than something that diverges, I diverge. The problem is you have to know what to compare to. And this is one of the situations where the more problems you do, the more familiar you are, the more examples you have, the more things you can try, the more things you can compare. And so the best way is to just do lots and lots of problems. The ratio and the root both involve doing an algebraic calculation. So this is looking at the limit as n goes to infinity of an plus 1 over an, and the other one is the limit as n goes to infinity of an to the 1 over n. And so when you're trying to decide, do you want to do the ratio or the root, usually people like to do the root test. I mean, the ratio test over the root test. It's usually the algebra is a little bit easier to be working with ratios than to be working with roots. If you are trying to do the root test, one thing that's often useful is to look at logs. So whenever you see a product, if you have taken a class with me, what should be your instinctive response? Logs. Take a logarithm. Okay? It may be a bad idea. And again, the standard example is teaching a third grader how to multiply. There will be times when it's a bad idea. But if you're doing a mathematical argument, if you're doing a scientific argument, you have an expression involving products, oftentimes taking a logarithm is much nicer. And what's nice is we talked about the logarithm, and it's an increasing function. So if you have two numbers that have a certain ordering, when you take their logarithm, the ordering is preserved. And so rather than studying a certain quantity, it's often easier to study the logarithm of the quantity. So if I know the logarithm converges to 5, then the number converges to then the sequence converges to e to the 5. If the logarithm converges to -1, then my quantity converges to e to the -1. So when I have an to the 1 over n, if this is hard to analyze, well, if I just take the log of everything, I would have with the limit as n goes to infinity of the log of the absolute value of an over n. And that might be easier to analyze. So who is our favorite New England transcendentalist writer? Thoreau. And what great advice does Thoreau give us? Be more specific. Simplify, simplify. So when you are trying to do any algebra, before you start doing a lot of algebra, stop and think, can I make the expression a little bit easier? You know, the ratio test, the root test, would it be better to take logarithms? Well, with the ratio, if I take logarithms, I get the log of an plus 1 minus the log of an, I probably don't want to have something like that. But with the root test, a to the 1 over n, it might actually be a lot easier to take the logarithm. Okay, so then it all comes down to which one should you try. What's nice is we don't have that many possibilities. And so what you do is you try one of the tests. I strongly urge you to try one of the tests on a separate piece of paper. And then if it works, then transfer that to the exam or to the homework. If it doesn't work, what do you do? Try another one. Do you throw away the piece of paper that you were using? No, you put that off to the side and you try something else. And hopefully one of the other ones works. And if none of them works, maybe you go back to one of the early ones and say, you know, maybe the algebra wasn't so bad after all. So let's try to do an example. So let's consider the following. So an is n to the k e to the minus n. Do we think this converges, diverges? When we look at the sum. What are your thoughts? So do you think it converges or diverges? Give me a reason why you think why it might diverge. Okay, so why might that make it diverge? So when you look at n to the k e to the minus n, which part gives you a thought that maybe it diverges because n is going to infinity? Yeah, the n to the k, maybe that's growing very, very large. What makes you think it might converge? The e to the minus n. So it turns out we've shown exponential is much, much better, grows much, much faster than polynomial. So if I want, I can look at this as n to the k over e to the n. Okay, instead of doing k, let's just choose a specific value of k. Let's take 8. I can do this more generally, but let's just look at n to the 8 over e to the n. One way to prove this is to use the comparison test. Is I want to show that this is less than or equal to something that converges. Well, I know e to the x is 1 plus x squared over 2 factorial plus x to the 8 over 8 factorial plus x to the 9 over 9 factorial plus x to the 10 over 10 factorial, and so on and so on and so on. So I know e to the n is greater than, I didn't do greater than equal to, n to the 10 over 10 factorial. Because I'm just dropping a bunch of positive terms. Well, then that means 10 factorial over n to the 10 is less equal to, is going to be greater than equal to 1 over e to the n. Right? I've made the denominator smaller, so the fraction has to be larger. Right, yes?
Could you explain why those intermediate steps are in that way?
No, doing a 10 factorial over n to the 10 is greater than or equal to 1 over e to the n.
Could you explain how you got that?
So I look at e to the x. And so if I look at just the term from x to the 10 over 10 factorial, and I drop everything else for a positive value of x, that's going to be smaller than e to the x. So e to the n is going to be greater than or equal to n to the 10 over 10 factorial. So do you agree with this part over here? Now I'm just flipping things. I want e to the n in the denominator and n to the 10 in the denominator. So I cross multiply. And so I get 10 factorial over n to the 10, moving this over, is greater than or equal to 1 over e. You see how I'm getting from here to here? So 1 over e to the n is less than or equal to 10 factorial over n to the 10. That means our expression here is less than or equal to n to the 8 times 10 factorial over n to the 10. So I'm just replacing what e to the n is. Well, n to the 8 over n to the 10, that's just 1 over n squared. Does the 10 factorial matter? In terms of whether or not the sum converges, does the 10 factorial? No. Think of it as just rescaling things. We know that term by term, this is less than a constant multiple of 1 over n squared. What do we know about the sum of 1 over n squared? Converges. So now we have converges by comparison to a p-series with p equals 2. And so here is a way to prove that this sum converges by using the comparison test. Is this an easy or hard proof? I would say it's relative. I am going to conjecture that there is no one here who is 23 or older. So I have been doing these problems longer than you've been alive. So for me, it's really not that hard to look at this and quickly see, oh, this is a comparison. I know e to the n is growing so rapidly, I can just pull off that term. This is how I knew to go to 10 and not 9. If I went to 9, I would have a 1 over n here, and I would have this less than or equal to something that diverges. If I had 11, I would have extra convergence. It's not hard for me because I've been doing it so long. That's the comparison test. The longer you've done it, the easier it is. The less you've done it, the harder it is because you need to know what to look at. And the idea is I have a lot of decay with e to the n, or e to the negative n. I have a lot of growth in the denominator with e to the n. I just need to go far enough to kill the n to the 8. So that's one way to do this problem. Any other questions on this one? Yes?
It was a general case that
So if it was a general k, I would look at the first integer that's 2 more than k. Yes. And so as long as it's a little bit safe like that, it's not going to be a problem. You just have to go just a little bit further. Any other questions on this using the comparison test? Okay, how else could we try to do this? We could do ratio test. And after we do it with the ratio test, what do you think is going to come next? Probably the root test. And after that? Now, there are other ways to do this with the comparison test. If you know that n to the 8 is growing slower than e, we know n to the 8 is equal to e to the natural log of n to the 8. It's e to the 8 log n. Right? So n to the 8 e to the minus n is e to the negative n minus 8 log n. When you put in the algebra. Which is growing faster, n or 8 times log of n? N. And so in fact, once n is really, really large, n minus 8 log n is greater than 1/2 n. Because when n gets really, really large, n minus 8 log n is essentially n. Okay, this is then the same as negative n minus 8 log n is less than negative 1/2 n. So I'm just being extremely careful not to screw up the signs. When you multiply by -1, you switch the ordering of the inequality. So that means e to the negative n minus 8 log n is less than e to the negative 1/2 n. Right? Or e to the negative n minus 8 log n is less than 1 over the square root of e to the nth power. What can you tell me about 1 over the square root of e? Smaller than 1. So comparison with a geometric series with r equals 1 over the square root of e, which is less than 1. So this is another way to do it with a comparison test. And in fact, this is going to give you a lot faster convergence than the other one. In the other one, you 1 over n squared, it converges, but slower. Here, we've got exponential decay. This is a better argument because the e to the minus n is dying much, much faster than e to the 8 is growing. And so this is to just illustrate that there's more than one way to solve these problems. There's more than one comparison you can do. It's a question of which way do you see the algebra, which way do you feel comfortable. And here I've got something with an exponential. Let me write everything as an exponential. And so I can write it as e to the minus. So I can write e to the log n to the 8, and that's the same as n to the 8. All right, so let's do it now with the ratio test. And again, for the ratio test to work, the limit has to be computable, and it has to either be strictly less than 1 or strictly greater than 1. So let's look at the limit as n goes to infinity of an plus 1 over an. I always like starting by writing explicitly what we're looking at. And so this will be the limit as n goes to infinity, an plus 1, so it'll be n plus 1 to the 8, e to the negative n plus 1, divided by n to the 8, e to the minus n. And now we just have to do some algebra. So it's the limit as n goes to infinity, n plus 1 over n to the 8, e to the negative n, e to the negative 1, e to the negative n. This is just e to the negative 1. Yes? So what is n plus 1 over n going to? Well, n plus 1 over n goes to just 1. But I have it to the 8th power. It's still going to go to 1. One way you can see that is let's look at the limit as n goes to infinity of the log of n plus 1 over n to the 8. That's the limit as n goes to infinity of 8 times the log of n plus 1 over n. What is, if n plus 1 over n goes to 1, what does the log of n plus 1 over n go to? 0. And so what does 8 times 0 go to? 0. So we know the log of this expression goes to 0. Ah, well, if the log of the expression goes to 0, then the expression goes to e to the 0, which is 1. So n plus 1 over n to the 8 goes to 1. And the same argument works instead of doing it to the 8th power, if we did it to the kth power. And again, this is the power of logarithms. You could, of course, write this, because 8 is an integer, as n plus 1 over n times n plus 1 over n times n plus 1 over n times n plus 1 over n, and do that 8 times. What's the limit of a product? If the limits exist in a finite, the limit of a product is the product of the limits. And so since I only have 8 products, it's a finite number. The limit of a finite product is the finite product of the limits. And so I could make this work. I don't have to take logarithms because this is a fixed number, I'm okay. If I replace this 8 with an n, it would be very different. N plus 1 over n to the n goes to e. And the other problem is you have more and more products. So this limit here is 1 over e, it's less than 1, it converges. Which is easier, the ratio test here or the comparison? I would say probably the ratio. You know, again, I've done the problem so many times, I know that this is growing much, much slower than e to the minus n, but it's still a little bit of time to write that down. Here, it's very fast to write down this ratio. And the only real challenge is given the n plus 1 over n. All right, any questions on doing this using the ratio test? All right, so next is using the root test. So I'll leave the word limit. Okay, so now we want to calculate an to the 1 over n. So it's the limit as n goes to infinity, n to the 8 over n times e to the negative n over n. I'm just taking the 1 over nth root of everything. Okay, what's e to the negative n over n? No. I'm sorry? E to the negative n over n. You're close. 1 over e. So this is just going to be 1 over e, the limit as n goes to infinity of n to the 1 over n to the 8th power. And so you can see that this is an expression similar to what we had before. N to the 1 over n is a calculation we've done previously. What is n to the 1 over n? What does n to the 1 over n go to? So it goes to 1. You know, if you take, for instance, n to be powers of 2, let's take 1024 to the 1 over 1024. What's 1024 to the 1 half? It's 32. So this is just 10 to the 10. I'm sorry, 2 to the 10. Right? So the 1 half is just 32. 1024 to the 110 is 2 to the 10. The 110 is 2. 1024 to the 1/20th is 2 to the 1/2 is the square root of 2. This is not a proof, but you can see how quickly this is coming down. I've got to do 1024 to the 1 over 1024. When I'm already at 1/20th, I'm already at square root of 2. So hopefully you can see that it's crashing down. And again, when you're trying to build intuition, choose a special number, choose a number that has good properties. You know, with n being a nice power of 2, I can easily take in repeated roots. Well, let's try to reprove what the limit of n to the 1 over n to the 8 is. We agree that if I just show that this limit equals 1, if I raise it to the 8th power, it's still 1. I can either write it as 8 products, or I can just do that log argument I did a moment ago. So we want to study the limit as n goes to infinity of n to the 1 over n. So when you see n to the 1 over n, what should you think of? I'm sorry? Logarithms. So instead, let's study the log of n to the 1 over n. And so we'll have the limit as n goes to infinity, the log, and if I take the log of n to the 1 over n, I get the log of n, I get the log of n to the 1 over n, which is the limit as n goes to infinity of the log of n over n. And this is one of the limits we calculated, which goes faster, n or log n, as n goes to infinity. N. And so this is just going to be 0. And so since this is 0, so if the log goes to 0, then the original quantity has to go to 1. And since that quantity goes to 1, it means we have 1 over e, and that's less than 1. I think n to the 1 over n is a slightly harder limit to do than n plus 1 over n. Yeah. N plus 1 over n, it's clear that that expression is going to 1. N to the 1 over n, you can do a little bit of work to convince yourself that it's likely that it's 10 to 1, but that's still more work. Okay. Any questions on the root test for this? All right, so the last for clean sweep is to prove this now with the integral test. So we would have to find a good function. And so that's going to be a little bit more painful. So I can give you an is n to the 8 e to the minus n. What should f of x be? All right, so now we need to integrate from 1 to infinity x to the 8 e to the minus x dx. Is this attractive? How would we do this? So we could do integration by parts on the order of 8 times. And if we do that, it will slowly move things down. So does anyone see that we could do it by integration by parts? All right, I'm going to try to do it a different way. I'm going to try to do it with dyadic decomposition. So this is more advanced. We talked about this when we were showing that 1 over n squared converges. And what I'm trying to do is just come up with a way to quickly estimate what's going on. I don't have to perfectly evaluate the integral, I just need to show that the integral is finite. So I'm going to look at the interval 1 to 2, 2 to 4, 4 to 8, blah, 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 2 to the n, so 2 to the n plus 1, and so on. Okay. So we'll see if this works. So I would have this sum and goes from 1 to infinity, the integral from 2 to the n minus 1 to 2 to the n, x to the 8, e to the minus x dx. And I'm just breaking the integral from 1 to infinity up into blocks like this. This is the sum, and goes from 1 to infinity. Now on this interval, x goes from 2 to the n minus 1 to 2 to the n. The largest x to the 8 can be is at 2 to the n. So this would be at most 2 to the 8n. Right? From this piece. And then I would have the integral from 2 to the n minus 1 to 2 to the n of e to the minus x dx. Okay. I'm just pulling out the largest x to the 8 can be. Oh yes, it should be in the comprehension. Okay. How large is this interval? To the n minus 1. So this would be less equal to the sum and goes from 1 to infinity, 2 to the 8n. The interval has length 2 to the n minus 1. And then, if I want, I could integrate e to the minus x, but I could also say, well, what's the largest e to the minus x as it comes over here at the end? This would be e to the negative 2 to the n minus 1. And so if I do an argument like this, I see that the initial sequence I wanted to study, the initial sum, I've converted to an integral, and then I've converted to a new sum. And now I have basically 2 to the 9n, and I have e to the negative 2 to the n. And so unfortunately, I would need to then show that that sum converges. And so that's a little bit more work. So this is not a great approach. What I could do is I have to argue a little bit differently. So instead of doing it like this, I need a better estimate, because that gave me a painful calculation at the end. So we're looking at x to the 8. If I just say, well, when x is large, x to the 8 is going to be less than or equal to e to the x halves. Are we comfortable with that? So if you're comfortable with that, then we have the sum from some point on with big N to infinity, the integral from 2 to the n minus 1 to 2 to the n. Well, actually, I'll just integrate from some big number n to infinity, e to the x halves, e to the minus x halves dx. Rather than doing a dyadic decomposition, let me just say that integrating from n to infinity of x to the 8 e to the minus x dx is less equal to this. But I can throw away a little bit in the beginning without anything being bothered. So it's just a negative x. well, this is the same as the integral from n to infinity of e to the negative x half dx. And that's finite. And you can just integrate the exponential function, everything is okay. So it all comes down to how can you approximate things. You know, sometimes an approach which works well in one problem leads you to something that requires a lot more work. So because the exponential function decays so rapidly, I have a lot of freedom in terms of trying to bound it. Rather than doing the direct integral x to the 8 e to the negative x, instead I could say, well, you know, x to the 8 is growing slower than e to the x half. And because of that, this integral converges. And so since this integral converges, then this integral converges, so the sum converges. And so this would be how to do it using the integral test. Notice that this is somewhat similar to the second comparison test we did. In the second comparison test, I basically said, well, n to the 8, I can write it as e to the log of n to the 8th power and do some kind of estimation like that. So it's very, very similar to that. When you look at this, I think the integral test is the least natural one here because I gave you x to the 8, because I gave you an 8 over here. If I gave you n e to the minus n, would it be that bad? No. You just need to know somehow that this integral converges. And again, if you think back to the first comparison test, your e to the negative x is 1 over e to the x. You'll have the x to the 10 over 10 factorial term here. So you can use that to gain convergence as well. So sometimes, instead of doing the integral exactly, we instead just need to do the integral enough to know whether or not it's finite or infinite. And that's a huge advantage. We don't have to evaluate it exactly. We only have to do it well enough to know, does it converge? Okay. Any questions on this? Okay. Any other questions on any of the other material? So again, any problem that you have, just carefully go through, piece by piece, all of the different tests. Hopefully, one will work. I don't want to start doing Green's theorem with on the order of 10 minutes left. So what I will do is I will probably save Green's theorem for Wednesday's class. I don't think we had any material that was planned for Wednesday's class. Let me quickly check. So I will save Green's theorem, and we will do Green's theorem in a day on Wednesday's class. And so this is essentially the class for those of you who are doing physics, or to a lesser extent, chemistry, mathematics. This is something you should see. And it's the real difference between 150 and 151. Because 150 does a lot on sequences and series, 151 does a leisurely introduction to Green-Bell-Stokes. We will do the Blitzkrieg one-day version, but that will be enough so that you can then have a sense of what the theorems are. I will end, since there's definitely a preponderance of people here today who are on the physics side, with one of my favorite physics thought experiments from special relativity. So have you ever seen anything on special relativity? Okay, so I have one of the best, I think, freshman physics classes in the country. And we did special relativity, I think, within the first month. At one point, the physics professor commented that everything we've done up until now has been Mickey Mouse high school physics. And we were just a little bit shocked because, we had already done not just special relativity, but general relativity. And this is Mickey Mouse high school physics. We then added electricity and magnetism to the special relativity, and wonderful class in terms of just the sheer amount of physics we got to see in our first year. And one of the best experiments, or thought experiments I ever saw, was to talk about how things are very strange when you're traveling at relativistic velocities. One of the quotes I still remember from my physics high school textbook is that if you look at the results of special relativity, they seem very counterintuitive. They seem very strange. But you have to remember that most people don't have experience traveling at 3/4 the speed of light. I like the use of most people don't have. I don't know anybody who has direct experience traveling at 3/4 the speed of light. Classically, we view velocity or speed as additive. If I have a train going at 100 miles an hour, and I'm running on the train in the same direction as the train at 10 miles an hour, how fast does it look like I'm running to somebody on the ground, on the station platform, as I go by on the train? The train's going at 100 miles per hour, I'm running on that train, 10 miles per hour on that train, to somebody on the ground, how fast does it look like I'm going? 110. It's not 110. It's a little bit less. The amount that it's less by, however, is so small that it wasn't until recently we could actually measure things well enough to see that speed is not additive. And you have to be extremely careful. It's very hard to prove things. It's much easier to disprove things, to prove that something can't happen, rather than to prove that something is actually happening. And what you really have is you have a physical theory that's good to a certain tolerance. That speed looks additive if the two input speeds are below a certain threshold, and it looks additive to within a certain tolerance. If speed was not additive, if you had a train traveling at the speed of light and you shined a flashlight on it, it would almost seem like that light should be traveling at twice the speed of light. So the closer you are to the speed of light, the stranger things happen. And it turns out that they talk about length contraction and time contraction. So as you travel faster and faster, your length seems to contract. So relative to somebody who's on the ground, if you're zipping by at 3/4 the speed of light, your length is actually reduced. What's fascinating is that contraction only happens in the direction of motion. There is no length contraction perpendicular to motion. And here's a beautiful thought experiment, one of the best thought experiments I've ever seen. So we are at the level of my ability to draw. We have a train traveling on tracks. And we will assume that the laws of physics are the same for observers that are in constant motion relative to each other. So imagine I have 2 cans of paint, and so if the train is at rest, the paint will follow the tracks. Okay? And now my train is traveling at, say, 3/4 the speed of light. And you hear the platform, you hear somebody waving as the train goes by. Imagine length contracted perpendicular to motion. Then this person over here would see the train inside the tracks. We will assume somehow the train is still able to travel. Maybe it's a jet train. Where does the paint land now? I'm sorry? Outside the track? So,
It doesn't hit the train.
well, so where does the paint land? Does it land inside the tracks or outside the tracks? You know, I've got 2 cans of paint at the very end of my train. So where does the paint land? Inside. So the person on the ground would see something like this with the paint inside. The person who is on the train, however, to them it looks like the tracks and the platform are moving. So if there's contraction, if you're on the train, you would actually see the train tracks contract. And now where does your paint land? We can slow down and we can re-enter the same reference system, the same coordinate system as each other, the same inertial frame. You can't have the paint both inside and outside. And once I pass this point, how my train is speeding up or slowing down can't have anything to do with where the paint is. And so because they have to be able to see the same thing at the end of the day, there can't be any contraction perpendicular to motion. So this is one of the most beautiful arguments I've seen in my entire academic career. I normally don't get the chance to talk about it in a math class. Given that I want to lead into Green-Gauss-Stokes theorem on Wednesday, this seemed like a nice place to try to put this in. We're also coming right after a sequence of lectures on the various tests for convergence. And it all comes down to trying to think cleverly. And that's one of the hardest things to do. The more examples you see of clever thinking, the better. This to me is absolutely brilliant. Why do you think he used trains in the example? If you were to do this example today, you would not do trains. When was special relativity? 1905. And so we don't have jets, we don't have rockets, we don't have massive cars going over the highway. Back then, it's natural to use a train as an example. I believe when Einstein won the Nobel Prize, he had 6 papers in 1905, 3 of them were a truly groundbreaking record. There was still skepticism on special relativity. They believe the mention, even though he has some things like special relativity that may be a little, he's done enough other great stuff that he merits the Nobel Prize. Anybody know the other stuff Einstein had in that greatly in 1905? Brownian motion. And I think it was the photoelectric effect. It was a really good year. And one thing to remember from this is, what was Einstein's position in 1905? Was he a chair of physics at an institution? He was a patent clerk. And this is one of the biggest problems we have in academia is when you get submissions, how do you know that this is a submission that's worth reading versus this is a crank submission? You know the story of Ramanujan and his mailing Hardy, his manuscript. Hardy was not the first mathematician he mailed. And it's a fascinating story where Hardy, at first isn't sure what to make of this. Theorems, well, they're not really proven rigorously, but the statements are just so compelling. He says, you're either a genius or a madman to write down something like this. And it's a really interesting question of what kind of mindset are you in as people try to present their work to you. All right, so this is a good place to stop for today. We will do Green's theorem on Wednesday.